To this point, we've used Boolean logic to either make Boolean algebraic expressions or to look at basic digital logical gates. And in each case, we're effectively taking a number of zeros or ones as inputs or trues and falses as inputs. And then we're producing as output an evaluation of the entire expression or an evaluation of the entire circuit. Again, either a 0 or a 1 or a true or a false. Well, in this video, we're going to look at how in code we can perform bitwise logic operations, the same Boolean operations, on the bits of our data. So we're used to using Boolean operations in code already, and we do it within conditions most commonly, say in if statements, while conditions, do while conditions, that kind of thing. And so we have the most common of these that we use are the and or, but occasionally we put in a not operator. And while the not operator only works on a single input, what the three of these do in common is that they're effectively evaluating their operand or operands as true or false, and then applying some form of logic to get a return of true or false as well. But it's just an individual true or false, right? Or if we think about that from the digital logic perspective, sort of like an individual 0 or 1. But very often we need to take a piece of data, which is a lot of bits, and we need to evaluate some subset of those bits, or we need to manipulate some subset of those bits. And to do that, we use bitwise logical operators because they're the same core basic Boolean functions that we see in digital logic. But instead of producing a single bit result from a bunch of inputs, what we do is we can take the operands and align them one over the other, as I've got here in the bottom of the slide. We can apply the logical operation to each vertically aligned pair of bits and then get a bunch of zeros and ones as output, all from one operation. And then we can store that output or immediately feed it into some other calculation for whatever purpose we might have. So I'm going to walk you through this one here that's at the bottom just so that we can get a bit of terminology in and see how this works. So there's two numbers usually involved in these operations, and they have to be the same length. So here I'm going to apply an AND operation at the bitwise level between these two 8-bit numbers. Now the top 8-bit number we're going to refer to as the original bit string, and the bottom one is known as the bit mask. The original bit string is the set of bits that we either want to manipulate or that we want to evaluate some subset of. The bit mask has the purpose of identifying which bits we actually want to deal with. And the way we do that is either by having ones in strategic locations or zeros in strategic locations, depending on the individual operation that we're applying. So in this particular operation where we're applying the AND operator, AND gives you a 1 only under that unique condition where all its inputs are 1. And so when I create a bit mask that has bunches of zeros around a set of 4 ones, effectively what I'm guaranteeing is by ANDing whatever bits happen to be in the original bit string that are aligned with the 4 zeros of my bit mask, I'm guaranteeing that I turn all of those bits off in the result. So you'll notice in my bit mask I have 2 zeros on the left, 2 zeros on the right, and in my result I have 2 zeros on the right and 2 zeros on the left. And that's a direct result, at least in part because the bit mask itself had zeros ANDed with something. That'll always be 0. Now from the other perspective, where I have ones, whenever we AND something with a 1, let's say it's a 0 ANDed with a 1, then we get 0 because 0 and anything is 0. However, if we AND 1 with 1, we get a 1. So 0 ANDed with 1 is 0. 1 ANDed with 1 is 1. So anything ANDed with 1 is itself. So where my bit mask has 1s, I'm actually allowing the original bit string to come through into the result. And that, of course, is a direct that's a direct result, if you want to think about the Boolean equivalence laws, the and form of the identity law, I'm pretty sure, where one ANDed with A is equivalent to A. We can look that back up, but I'm pretty sure that's what it is. So this is the basic way we're going to apply it. And everything happens in those vertical pairs of equally positioned bits. So now what we're going to do is go through all the individual logic operations and look at what the symbols you'll need to use in code are and give some very small example code. So we'll do this quickly. To perform AND across a bunch of bits into variables, we're going to use the single ampersand. Don't get that confused with the double ampersand that also performs the AND operation at a logical level. We're not looking for true and false typically when we're applying a bitwise operator. So we have to keep the way we write them separate. So single ampersand. And what we're going to do for each of these examples is assume that we're using 8-bit integers. That way we don't have to worry about a bunch of extra leading zeros on one side, for example. So I've declared two unsigned integers x and y. And I've given them hexadecimal values. In the first case of x, it's hex 76. In the case of y, hex B4. Now, I don't like to normally just assign raw hexadecimal immediates to variables. And there's not enough time in this video to cover that. But in a video upcoming, I think it's called Creating Superb Bit Masks, we will walk through why we don't want to do that and the way that I create my individual bit string values from scratch. Okay. In the meantime, we'll correlate this x, which is hex 76, up here to the top row. And so this top row is the bit pattern for 76 hexadecimal. And the bottom row of our original operands is hex B4. So when we want to apply the AND operation, we just throw a single ampersand in a line of code as we have here. So I'm going to do the AND bitwise of x and y and store the resulting bit pattern into z, which is also going to be the same size because it's the same data type. So if we look to the example on the right, we see that AND works the way we would expect. Remember, the truth table for AND says that the only way to get a 1 in the output is for all of the inputs to be 1. So we're going to see that over here in each column. So the only ones we'll find in the output, here, here, and here, are going to be in columns where both bits in the same positions of the input are also 1s. So we can see that here. The OR operation, which looks an awful lot like how we apply the OR operation for logical conditions, is not two vertical pipes, but one vertical pipe. With one vertical pipe, we're applying the bitwise operation of OR. So again, we're going to use the same values for x and y, but this time we're going to capture the result of doing a bitwise OR between them. So OR will produce a 0 when all of its inputs are 0. And then if one or more inputs are a 1, we're going to get a 1 as output. So the unique condition really with OR is that we're only going to get 0 when everything else, when all of the inputs are 0. And so we can see that here labeled in this example. So in the columns where we have 2 zeros on the input, we get 0 in the output, and every other bit of the output is a bunch of 1s. The exclusive OR operator, when we apply it at the bitwise level, and we don't typically do anything like this with logical conditions, we only do this with bitwise operations. We use the up caret, so the thing that you might use to represent in a text message in exponent. The up caret tells us to perform the exclusive OR operations between all vertically aligned set pairs of bits. So with exclusive OR, remember that we're looking for one and only one of the inputs to be a 1 in order to get a 1 as output. So whenever we see a mismatched pair of input bits in a column, we're going to get a 1 as output here. So we can see that here. 0 and 1 gives us a 1. 1 and 0 gives us a 1. 1 and 0 gives us a 1. In all the other columns, the pairs of bits are all the same. And so we're going to get zeros as output, regardless of whether those pairs were a pair of zeros or a pair of 1s. That's just the nature of exclusive OR. The inverse operator, which we also call NOT when we're looking at digital logic sometimes, the inverse operation, we're never going to refer to this as NOT. NOT in code really means the exclamation point, right, the bang, that's used for logical conditions. We don't typically refer to it as NOT when we're doing bitwise operations. Instead, we'll say inverse. And that's because inverse takes one operand, some bit pattern of an arbitrary length, and it flips all of the bits. It inverts the entire bit pattern. So we have a very simple example here where we take our bit pattern for 7/6 hexadecimal, and then we invert it to the output. If you, at least the way I always visually inspect that this kind of thing has happened, is if I start on the left and find a 1, whether it's in the input or the output, and then just follow the ones, I'm sort of forced to do like a little snaky pattern, but there's never a point where there's a 1 above and a 1 below, because the whole thing is always inverted. And the same pattern holds with the zeros. Now, we also, in needing to manipulate or evaluate bits, we'll sometimes need to do other operations that are not really Boolean operations or logical operations directly. And those are our shift operators. So we have bitwise shift operations that we can perform as well. And effectively all this means is that we take some set of bits, and we just slide them over like marquee lights, either to the right or to the left, however many bits we desire, although usually we do it some number of positions that's smaller than the size of the container that our bit pattern is in. Because if you have a 8-bit pattern and you slide all of the bits off to the right or off to the left 15 times, it's really unclear what the purpose of that would be, since you've effectively discarded all of your bit information. So when we slide bits around, we have two big problems. The first of those is all these bits fit in the container that they're held in to begin with. And so if you slide to the left, if you slide to the left or slide to the right, even a single bit, then some bit of information is going to go out of range. So we have to know what to do to deal with those. Now, out of range bits, whether it's 1 bit or 4 bits or 7 bits, they're just discarded entirely. They go to the bit bucket. But the other problem is as we slide bits along, so I've got all these bits here, and let's say I shift to the left 1 time, then yeah, this outer bit here kind of goes away, but a vacuum is created over here. There's a hole where there used to be a bit, now I've slid things over. And that has to get filled with a 0 or a 1. And if we make more than 1 bit hole or 1 bit vacuum, they all have to be filled in with something, either zeros or ones. And we have a couple rules about how we figure that out. First of all, if the vacuum is in the lower order bits, or the right end of your bit string, we are just arbitrarily going to put zeros in there, no matter what other conditions we have. If it's on the low order, we always fill vacuums with zeros. If it's on the high order, and we're dealing with unsigned data, we will also fill in that vacuum with zeros, the high order bits being the left end bits over here in your number, right? Where it gets a little bit unusual is if we have a signed value. So if the data type, not like our examples where I had unsigned ints, but if I had a type like int, that's a signed value, right? Ints can take on -5 or -20. So they can be positive or negative. If we have signed data values, then when we apply the shift operations, particularly shifting to the right, we're going to end up with a vacuum on the left. And what we're going to fill that vacuum with is duplicates of the original signed bit. That way, when shifting to the right, some signed variable will actually maintain the original sign. So if it was a negative number and we shift it to the right 3 times, we're still going to have the original 1 in the sign bit location, or from the sign bit location shifted over 3 times this way, but the 3 bits of vacuum are going to be filled with duplicates of the 1. If it was a positive number, then the bits of vacuum will be filled in with zeros. And that's, if you'll recall, called sign extension. So I have some examples down here at the bottom. We have our 7/6 hexadecimal bit string on the left of each of these examples, and in the top one we're doing a left shift of 3 bits, and as a side effect we're going to both discard bits as well as fill vacuums. So you'll notice here I have 3 bits listed all the way to the left edge, and when I shift to the left 3 bits, those 3 bits, 0, 1, and 1, are just going to be discarded off to the bit bucket. The vacuum will show up on the right, and it'll be 3 bits big. And whenever we have our vacuum on the right-hand side, we just fill it arbitrarily with 0. Now the bottom example shifts to the right 3 bits. So we at least know that the rightmost 3 bits, 1, 1, 0, are going to be discarded to the bit bucket. Then we'll have a vacuum on the left, and that needs to be filled. Now it matters whether or not this is a signed variable or an unsigned variable that we're shifting. And it may look like I've construed this example by putting a 0 in the highest bit, or where the signed bit would be located in the original location, so that we end up with zeros in replacing our vacuum. And we don't really know whether it was signed or unsigned, so that we don't have any ambiguity. But that isn't quite true. If you'll notice down here in my actual example, when this Google Slide stuff goes away, I have the hex number 76, and I'm right shifting that by 3. When I say hex 76, that's not any different. It's a numeric immediate. It's no different than if I wrote code that said 5 or -15. So at least in C or C++, when you put an immediate numeric value like that, it's going to be interpreted as an int, and that is a signed value. Now it is a coincidence that my particular signed value would have been treated as a positive one, and so by sign extending we would get zeros to fill the vacuum. And that's the same thing that would have happened if we treated this as unsigned, but we must always understand that whenever we write an immediate, unless we do something to cast it to an unsigned value, it is signed, and that means that we can run into problems when doing right shifts on them. So be careful. All right, so here are some more examples that make it extra clear the difference between the signed and the unsigned versions of shifts to the left and to the right. So we have the same hexadecimal value being stored in a pair of unsigned integers, the ones we've been using, hex 76, hex B4. We put those into a pair of unsigned integers, and we put them into a pair of regular integers, which are signed. Then we'll start with hex 76. So in these two examples here, we're taking hex 76 and left shifting it 3 times. The only difference is, in the top one, we're left shifting hex 76 treated as an unsigned value, and in the bottom we're treating it as a signed value. But when we shift to the left, we are always creating a vacuum on the right-hand side, and as a side effect we will always just fill it with zeros. So when we left shift, there's no difference at all in the effect between signed and unsigned values. However, when we shift to the right, then we see the need to distinguish between signed and unsigned values. So down here at the bottom, where I take x and I shift it to the right 3 times, x is an unsigned value, so we end up with zeros being brought into the high order bits. When I shift to the right on z, since it is a signed value and it contains the bit pattern B4, which does have the signed bit containing a 1, so it's really a negative number in our 8-bit system. When I shift that to the right, my vacuum of 3 bits gets a copy of the original signed bit, which was a 1. And so we have 2 very distinct differences in what would otherwise appear to just be a hex 76 right shifted 3 times. But because one time it was signed and one time it wasn't, we get 2 different values. So remember to take care when you're doing this. One rule of thumb I like to do is make everything unsigned when I'm doing a bunch of shifting. And if I need to ensure that I'm copying the original signed value, then I sort of have to break my pattern and use a signed value. And that makes the code stand out to me, because because it looks different than my other code, which helps me notice it, right? Or helps me notice when I accidentally do it as well. Now, there are other times when we want to use shifts on signed variables, and that's actually to perform math. And it's the reason that we sign extend rather than just filling those vacuums with zeros. Right? So if you take and left shift any bit pattern by 1, and it's a signed bit pattern, that's going to be the same as multiplying it by 2. And you can think of this very trivially by writing down a bit pattern like the bit pattern for 3. If you have a positive 3, you've got lots of zeros and then a 1 and a 1. And if you were to left shift that just 1 bit, then you'd have lots of zeros, a 1 and a 1, and then a new 0 on the far left that you just filled in, right? And 1, 1, 0 is the number 6, which is twice as big as 3, the original value. And that's because we're relocating everything to higher orders of the base, right? The same thing's true when we do it with decimal numbers. If you take a number like 13 and you shift it over to the left by adding a 0, you've basically multiplied it by 10. So shifting left 1 bit multiplies by 2. If you shift left by some greater number of bits, n bits, you're basically multiplying by 2 to the nth power. Now the opposite of that is true for right shifts. So when we do right shifting, if we shift 1 bit, we're doing division by 2. Right? But you have to take care and look at your results to see how the remainders are discarded with this when we're comparing the difference between what happens with positive signed numbers and negative signed numbers that we do division on this way. So you might do a little experiment to figure this out. So shifting to the right 1 bit is division by 2, and shifting to the right n bits is division by 2 to the nth power. Right? And as a side effect of doing this of thinking this way, we always want to do this stuff if we're doing math only with signed representation, because then the shift operators are always effectively performing a mathematical operation for us. Well, that's it for this lecture. I hope you've learned some interesting things about how we can apply Boolean operators at the bit level, which we call bitwise operators in code. In future videos, we'll look at how to create bit masks to find interesting information or manipulate parts of other data directly.